My name is Katerina Deliali and I'm a project officer in CINEA. I have some projects in my portfolio focusing on road safety and mobility, and FLEXCRASH, which we will hear more later, is one of those projects. I'm very happy to welcome you here. We have nice presenters. We have Thilo, a really nice moderator to facilitate the discussion. Some background on this topic of materials for light and green vehicles that are also safe. So may I have the next slide on the screen? Thank you very much. So why do we have these projects? There is a focus to better understand how materials from which we construct vehicles can be lighter, more circular, and overall greener. So there have been two calls for that, one launched in 2020 and one launched in 2021. And essentially, we see that there is a follow-up. So we started in 2020 focusing on trying to reduce the vehicle weight, setting the target of achieving 10% at least, but also reduce the production time, facilitate a faster production process, and so on. And then we have the next year a new set of projects also focusing on lightweight and advanced material for the automotive industry, but they also incorporate the aspect of safety. And safety very specifically looking some years ahead and focusing on automated vehicles and what will be the situation there and what would be the safety issues and how a car should be manufactured to be able to tolerate those safety issues. So this is a bit overview. Then I don't want to take more time on that because we started a bit late. I would like to give the floor to Dr. Alvis Bianzin, who is a material scientist working at MBM Nanomateriala in the field of power metallurgy and nanotechnology in industrial processes. So the floor is yours to talk us about the FLAMINGo project.
Thank you. So, good morning, everybody. FLAMINGo, as already said, is focused on bringing metal matrix aluminum nanocomposites into vehicles in order to identify the pathways to reduce the weight of the entire vehicle. So I'm here with my colleague Raquel Riccio that will talk more about the results in terms of LCA. But now a bit of numbers that regard FLAMINGo. We are 11 partners. The project started 4 years ago and ended a few weeks ago. This is a consortium in which there are a few universities, actually only Brunel universities, and a couple of technology transfer research centers, one in Austria related to foundries, another in Portugal related to welding, and all the other partners are industries in the field of materials. And that's allowed us to have an overview of the entire life cycle of these materials and their implementation into the cars. Thanks to the fact that we are at the end of the project, I can give you also some more numbers. And for example, 100 kilos of nanoparticles master batches has been produced. And this delivered 3 tons of aluminum metal matrix nanocomposites that has been produced and used throughout the process. Also, 200 kilos of these has been recycled to test all the implications around that. And 6 processes related to aluminum manufacturing and processing, casting and forging has been used and tested throughout the project. So this led to a total of 4 components that has been installed in the vehicle. I have one of the components on the table there. It's a steering knuckle, and this allowed us to do some calculation on what was the actual reduction on the vehicle, and also some projection on what this can mean for the entire vehicle. At component level, we reached quite high weight reduction, but of course one component is not enough to reduce the weight for the total vehicle. Since the target for this call was to reduce the vehicle weight by 10%. So FLAMINGo was focused on one material, which is the introduction of aluminum enhanced by inoculation of nanoparticles. The idea was we can substitute part of the steel structure, the steel component in the car, and obtain an actual quite substantial weight reduction. But of course, the inoculation of nanoparticles brings a lot of questions around the safety for workers in the value chain of manufacturing the cars and manufacturing the components, and sustainability from the point of view of the cost of these nanoparticles. And we had to test for this the entire manufacturing and life of these components, from cradle to grave and back to cradle. We wanted also, and we succeeded in including these components in a real vehicle and tested for some 100 kilometers. So I will focus the rest of the presentation of some of the results that we achieved, because in 4 years, 4 years cannot be squeezed into 15 minutes. And one of these is about the approach that we had. So solid state by design is something that we wanted to exploit as much as possible. So we concentrated in 3 kinds of nanoparticles that were there since the conception or inception of the project. All of these had pros and cons. Silicon carbide has a good density compatibility with aluminum, but cost for the nanoparticles is quite high. Titanium carbide, on the contrary, is problematic from the point of view of density compatibility, but cost is lower because we managed to develop a process to make the titanium carbide particles directly into the metal matrix. So we obtained highly concentrated master batches of aluminum with nanoparticles that can be safely inoculated in a different process of casting and then forging extrusion of aluminums. Similarly, the idea is also to take on the market nanoparticles, silicon carbide in this case, and mix it with aluminum at solid state process. And in order to create these master batches that can be, again, inoculated in casting and then forged and extruded. So this process, we, as a company, we dealt with it. We used mechanochemical alloying to, at solid state, in one case, create the nanoparticles of titanium carbide. In the other case, obtain a predispersion of silicon carbide and aluminum. So, well, yeah, I didn't talk about aluminum oxide that was scrapped quite soon. So in the project, we had to verify 4 hypotheses, one of which is that the addition of nanoparticles does not compromise existing recycling processes. We don't want to put in the market something that can mess up with the currently existing practices. So we want also to check that these nanoparticles can be completely removed from the recycling process. And for this, we planned to use expandable nanoparticles, so something that we can waste during the recycling process without impacting too much on the cost of the process, of the entire approach to the material. Then we want also to verify that using these embedded nanoparticles in master batches are safe to use throughout the different processes, and that the use of these master batches is effective in predispersing the nanoparticle. So on the first point, we reach quite good results. Conventional recycling, we proved is enough, sufficient to remove the nanoparticles. And we validated that. What you see in the chart is basically a measurement of the hardness of the material obtained in the reference is the standard aluminum. The second column is the one with the inoculated nanoparticle, and then has been recycled, going back to the original hardness. Hardness is one of the methods we use when these chemical methods cannot be used due to similar elements present in the aluminum matrix and in the nanoparticles. As regards the safety, we also got good responses in the sense that we managed to monitor all these steps in which nanoparticles and master batch has used. This is the making of the master batch, the inoculation during casting, the use in LPDC, low pressure die casting, and the use of these master batches in direct chill casting, the extrusion process, and also the recycling process. We were there, a partner were there, monitoring the release of nanoparticles in each of these processes, and what we saw is basically that there is no difference from the normal practices. So the same amount of dustiness and nanoparticles that are monitored in standard processes, the same of the processes when using this addition of nanoparticles. As regard, is it effective as a pre-disperse means? Well, there is not space enough there to to answer this. This is just some line of activities that has been performed in the project. We tested silicon carbide by green side casting, and this led eventually to the production of those components, and we managed to use topology optimization and then the modeling of the mold to obtain good performances at lab scale and also at the, let's say, prototyping scale at component level. This weight reduction refers to the weight of the original steel component for which we had access to. Silicon carbide has been used also for low pressure die casting, just on lab scale. And here we can see something that was interesting and not correctly expected at the beginning of the project. You can see in the S-cast we have two columns, that is the hardness of the material, and the S-cast with the nanoparticles is much harder. So the mechanical performances also related to that are much higher. Once annealed, this difference is lost because the aluminum alloys are originally designed to refine the nanostructure through annealing. So basically the nanoparticles we were inoculating are competing with the ones that are obtained during the annealing of the components. And we tested titanium carbide on high pressure die casting. We missed the aim area in which we were planning to arrive in terms of properties of yield strength and elongation. And then we got good results in terms of gravity casting with yield strength increase about 8 and 20%, but we couldn't translate properly that into the DC casting. This was a problem related to the actual manufacturing process. So instead of having the correct number of nanoparticles in the alloy, which is, by the way, is around 1%, we ended up with a bit lower amount. So the final properties of the material were not the same as the lab scale one, but we managed to get an entire rear frame produced with this technique and install it in the vehicle and test it on the field. So now I'll leave the floor to my colleague to talk more about what we calculated from the LCA point of view on the vehicle and the concept around it.
Yes, hello everyone. I'm Raquel Recia. I work in Global Factor, and I was in charge of developing the life cycle assessment in the work package 8 of this project. So here we have the vehicle that we analyze. One of the main tasks or objective of the project was, in one hand, to analyze the environmental impact of the demonstrators that were developed during this project, that were two steering knuckle and one rear frame, but also we analyzed the life cycle assessment considering all the life cycle of the vehicle. So we not only consider the manufacturing side, but also other phases like the assembly phase, the use phase considering the electricity consumption of the vehicle, and the end of life. So here we have the base scenario, that is the ATX4 vehicle with a weight of 1,171 kilos. This is the base scenario that is composed with steel metal parts. And then we have the FLAMINGo approach, that is the vehicle where the two steering knuckle and one rear frame were replaced. So doing this replacement, we achieve a 45% weight reduction on component level, a 7% overall weight reduction considering the metal parts, and a 2% of weight reduction considering the overall vehicle's weight. So then one of the main objectives was to analyze what was the influence of replacing the steel parts in the vehicle. So we developed 4 more scenarios or analysis in this case, and here we changed the type of metals that were in the metal side of the vehicle. So in the third and fourth scenario, we consider a 50% of substitution with aluminium metal parts. And the main difference between third and fourth scenario is the recycled content of aluminium, because in the third scenario we have a recycled content of the 42%, and in the fourth scenario we have a recycled content of the 90%. So similar in the 5 and 6 scenario, here we conducted an analysis considering a 90% of replacement of the metal parts with aluminium, with nanocomposite, and the same as the third and fourth scenario, we varied the recycled content of aluminium from 42 to 90. Here we have the main conclusion. If we see the chart and the table, we can see that that the substitution of these steel parts with aluminium, we can obtain a 2% of the reduction in weight, but also we can achieve a energy consumption reduction in the use phase. We estimated it. And if we move to the other scenarios, to the third, 4, and 5, and 6 scenario, we can achieve more reduction, in this case, from 15 to 22. And then, if we look to the environmental impact, we can see that FLAMINGo approach has a slight increase in the overall impact. This is because the manufacturing side, because the aluminium part, the manufacturing part, the environmental impact is higher than the steel part. But if we take into account the overall the whole life cycle, we can see that the use phase is one of the main contributors of the life cycle assessment. So if we can achieve a reduction in weight, we can achieve also a better environmental performance in the overall life cycle. So thank you.
Yeah, thank you. I move along because we are already quite late. As I told you, there are a lot of interesting details about the process that we are eager to share, but time is what we have. So the impact that we meant to arrive to is to allow a sort of redesign of the vehicle. All the figures that we have shown about LCA are specifically tailored on this kind of vehicle, but we prefer to have a specific vehicle to do all the tests in order to be quite realistic on the outcome. So the weight reduction is just the tip of the iceberg in terms of what we achieved. What we achieved also was establishing guidelines for the use of this kind of materials, start interacting with the standardization bodies in order to have changed also the way to speak, a way to recognize this kind of materials. And we proved that including nanoparticles as a strengthening means is not problematic from most of the processes, not for the recycling, and also for the safety around for the use of nanoparticles has been tested, and it is positive. One last message is that introducing a new material really has to consider the entire life cycle of this material. In this case, it's in the vehicle, and going through all of this allows also to think about the different interaction of the different processes and optimize the material in a global view. And thank you for listening to us.
I forgot to introduce Raquel. I thought I would have a tiny slot of time before. So this is Raquel Recio Paule, and the reason that I'm introducing her is that it's, of course, the other lady in the panel, but also she's not in the program. So her background is on chemistry and polymer chemistry, and she's now a senior climate change consultant working on life cycle assessment and environmental impact assessment. So now I give the floor to FLEXCRASH project represented by Christian Kurzbock, who is an industrial engineering in background, working in Virtual Vehicle Research Center in Graz, Austria. And he is now deputy leader in structural safety and lightweight material department. So Christian.
So thank you very much for the kind introduction and for the opportunity to present our EU project FLEXCRASH on this RTR conference. FLEXCRASH has, let's mention that before, two sister projects, that's Salient, that was presented last year, and also Heidi. And FLEXCRASH, as the title says, is working on a flexible and hybrid manufacturing approach to reuse aluminium in adaptive and tailored crash structures. So, general overview, where we started. We started nearly 2 years ago, so we are a bit over half time. We have budget about 4 million euros. With 10 partners from 5 different countries, a quite good mixture from research institutes, universities, and also industry partners. It is coordinated by EuroCAD, so I stepped in here for my colleagues from EuroCAD today, and will present our preliminary results since 2 weeks ago. So where are we now? What are we doing? We try to use recycled material in different front-end crash structures, and use this material in different manufacturing technologies. So we want to combine and hybridize different production ways, the different production paths, with an innovative manufacturing approach. And we use, as I mentioned before, recycled aluminium to do that, so that we can also can be more sustainable and for future crash scenarios, or for future crash structures and components. So what is the research beyond the state of the art? We have two different main topics that we want to tackle at the FLEXCRASH project. This is the vehicle lightweighting and also passenger safety. The problem with these two focus on a project is that vehicle lightweighting and passenger safety didn't fit together. So when you're doing lightweighting, especially on the structural side, the passenger safety decreases because weight always is the best point to save passengers, to enhance the passenger safety. And when we lightened the structure regarding lighter materials, optimized structures, and so on, we have to rethink a little bit the safety concept. And we want to do that with this manufacturing approach that will I show in the next slides, and also with an active and adaptive system in the car that enhance the passenger safety. So what are the objectives or the solutions we are working on? In total there are 5. The first one is the crash simulation. So to enhance design and component design, and to speed up the development process, you have to be there quite precise, you have to be there quite predictive to have an forecastable crash simulation on these used materials. The second point is, as mentioned before, the flexible and hybrid manufacturing processes with these newly adapted materials. The third point is then the outcome, so the new crash-tolerant structures with an adaptive or with an active system in it, and also lighter and safer for the passenger and for the vehicle. The fourth point is advanced testing. So when you're using a new material, especially recycled materials, you have to possibly rethink the testing procedure on coupon level, also on component level. And the 5th point is then the future needs for these crash structures because of an evolving world with ADAS system and with more autonomous vehicles in the traffic. We will have to rethink perhaps some of these crash scenarios. What we also did there in the survey and in the research from also former EU projects, and that is also part of the FLEXCRASH project, to show how these crash scenarios could be changed in future and how to react on this change of the crash scenarios. So the first topic is, as mentioned at least before, the future relevant crash scenarios. What we are looking there is how these scenarios will change in the future mixed traffic in a city scenario. How these severities will change, how the speeds will change. And therefore, the project partner from IMC Grams designed a scenario generator filled in with crash simulations and data from actual situations then improved it with other system, with different autonomous driving scenarios, and from these scenario generator that we have there, we evolved to different scenarios. So what could be relevant future scenarios that we have to react on? We find there are 3 different crossing scenarios which could be an issue in the future, or even more severe in the future. So these are the 3 scenarios, and we configure these 3 defined scenarios what we are testing our front-end structure that we will develop and optimize. So that's one of the points. The second point is also the manufacturing part of the FLEXCRASH project. So we will try to hybridize these manufacturing technology. So we use at the one side high pressure die casting and extruded profiles that we want to adopt with an 3D printing technology to enhance and to optimize the crash performance and also lighten up the use or the design structure. Therefore, we have our project partners from EuroCAD and also from EVS Fraunhofer who are working on these manufacturing part. Here you can see some of the examples how to, the optimization process with these 3D printed recycled materials, which is actually ongoing. And with these manufacturing technologies, with these optimized structures we can develop with these manufacturing technologies, we are thinking that we can lighten up the front end structure, and also enhance the passenger safety. Also, one part of the designing process, as mentioned before, is the virtualization. So we have to prove that our simulation models that we are generating, the methodologies, the tools that we are delivered to our project partners are, at one hand, accurate. On the other hand, these simulation projects, these simulation tools are robust and predictive. And what we can see here is just one front-end part. At the upper side, it's a normal extruded profile. The lower one is with an 3D printed pattern on it. It's just a few lines, for example. And we can see here an improvement about 30% on energy consumption on just this one part. And we are actually working on different patterns and to optimize these structures regarding different crash angles, regarding different crash scenarios, and then use that, as also mentioned in the topics before, and to test it on coupon level, to see the performance, to just take a look on how these 3D printing technologies influences the base material, and in the end, optimize the front-end crash structure. What are the mid to long-term impacts that we want to generate from the FLEXCRASH project? Is on the one hand the adoption of the future crash scenarios. So nowadays you have these on the right side, on the left side, these passenger safety regulations that we have to fulfill. But in the future mixed traffic scenarios, these scenarios will become extremely large. You cannot test all of these. You have to simulate it. You have to prove that your simulation is correct. And the only chance to fulfill such large testing requirements is on a virtual validated model. And perhaps a scenario generator like we created to enhance the safety on a future vehicle or component. The second point is to enhance the vehicle safety itself. So in FLEXCRASH, we try to improve, or we want to improve the passenger safety with two different approaches. One of them is the passive safety approach. So we want to optimize the passive crash structure. The second part is also this active system that has to be integrated, which we are actually working on. So this is an ongoing process. There we do not have so much data actually, but we want to combine these two T2's world for the pedestrian safety, for the occupant safety, and this is one of the mid to long term impacts. And at least we have two impacts on the manufacturing technology to optimize these manufacturing technologies. And also on the environmental side, the sustainability by using recycled aluminium. So these are our preliminary results from the FLEXCRASH project, and thanks for your attention.
Okay, thank you, Christian. Before we continue with the panel discussion, I wanted to see if anyone from the audience has a question for the speakers. Yes, please. Is there a mic? I'm not sure.
There should be a microphone.
Lucy, he's here. Yeah, with the light we cannot see.
Thanks. So it's Fernando Sanchez from IMEM. It's a question for FLAMINGo. Well, first of all, thanks for the presentations, very interesting. In the case of FLAMINGo, just a question, the distribution of the nanoparticles has experienced good results in all the casting procedures, all the casting processes that you have tested. And the second question is about, you mentioned at the beginning that you also tested the welding processes for this. So also to understand which are the results of the welding of these materials. Thanks.
Thank you for the question. So, is it on? So, yeah, okay. Well, we optimized the dispersion on all the casting systems using ultrasonication, special steering. The one with which we struggled more was the direct chill casting, simply because the material is poured into the mold. So, and with that system, we were using titanium carbide, which has a problem of density. So it basically was sinking before actually being delivered into the mold. That's why we ended up with a lower percentage. But in terms of dispersion, it was sufficient to obtain the enhancement on the mechanical properties that we hoped for. And the welding, yeah, I didn't include the welding. The welding we tried on two different, joints of all kinds, especially on the extruded parts, and they were all fine. We were expecting that also because there are some, on the market already there are some wire for aluminum welding that already contains nanoparticles exactly for the reason of being able of enhancing the strength of the material without requiring an annealing afterward.
So are there further questions from the audience? Yeah, Reinhard.
Hello, Reinhard Hackl, voestalpine. Thank you for the presentation. I have a question to the FLAMINGo project. So you did a topological optimization and a material change. So can you split up the weight saving into these two special parts?
Yeah, I think there was a little number in brackets in one of the slides. So on the steering knuckle, most of the weight reduction came from the topology optimization. We could do that because it was a green sand casting, and actually the mold was 3D printed. So we had the flexibility to test different configuration, even complicated ones. But eventually we had to consider the feasibility point of view. So we moved from a maximum of topology optimization down to the current component that you can see here, which the topology was mitigated, compromised, let's say, from considering what could be an actual mold made on steel. I don't remember the percentages at the moment, but over 2.9 kilos of the final component without nanoparticles. We redesigned it in order to consider the increased hardness and mechanical properties due to nanoparticles, and we reached 2.6 kilos on the steering knuckle.
Following up this question, did you also then, the reference for steel, did you also then compare if you did the topology optimization with conventional aluminium?
We did the topology optimization with the standard alloy base.
Yeah.
We are using 382, or if I recall correctly, and then we included the mechanical properties, increase of nanoparticles that we tested, and redo the topology optimization just to correct for the thicknesses, and it was not a big change, of course.
Okay, further questions? If I don't see question here, then it's my duty to bother the presenters. First of all, I also would like to thank you all three for the nice presentation. I remember that FLAMINGo has been presented also in one of the earlier RTRs. From the recycling point of view, you mentioned that you are removing the nanoparticles, correct?
Correct.
How are you doing this? And if you do closed loop recycling, is it then really needed to remove the nanoparticles?
Well, hopefully for a closed loop recycle, it is not needed. But we consider that a closed loop recycle could become a reality in the longer term, when a lot of components are made with this same material. So it's not actually feasible in the short term. So we wanted to test first what happens, can we remove it, and basically introduce in the market this kind of materials without messing up with the current practices. So that was the reason. And basically they can be removed as other impurities are removed. So by scrapping, they are seen by the recycler as oxide, and they're collected in the scrap.
Okay. And you're also using secondary aluminium to create your master batch? And do you have then to adapt the composition of the nanoparticles?
No, we had not. There was no problem in using recycled aluminum because it's basically as good as the primary aluminum. We were using just aluminum for the master batch production, but we have the possibility in the master batch production of including not only aluminum but also other elements, and then compensating for any change in the composition.
Yeah. Okay, thanks a lot. Now I have a question for Christian. You said that one of your main approaches is 3D printing to improve the crash worthiness of the components. As usual, when you're talking about 3D printing, what about the mass production? Is the process feasible for mass production? And you have you need it on rather complex structures.
Yeah. Mass production for 3D printing is always a difficult part. I think what we can show with our designs and with our manufacturing technologies, especially from Fraunhofer, that we can improve the safety massively on single parts. The technology itself will not work for the whole vehicle. So we will just let's say redesign or improve the crash safety on needed parts, and the most of the crash structure or the safety structure of the car shouldn't be it wouldn't be possible to improve with these technologies.
If I understood, you use on the crash structure, which are, let's say, extruded parts, and then you do the 3D printing.
Yes.
Are you also investigating to do the 3D printing first on metal sheets and then form it into, let's say, into a tube?
So
combine it then with welding?
The other way around, no. So the approach is to have a base material. To optimize also this base material, because you can lower the thickness when you improve with different patterns, and then just print these patterns for the supposed crash scenario or for the loading case that we will expect from these future scenarios. Yeah. But not only on the extruded parts, this also can be done on the high pressure die casting parts, because when you have some fancy optimized parts in the front end that won't be able to cast in one shot, let's say, then you can add these added features with a 3D printing process.
Yeah. And can you outline what are the biggest challenges in combining these manufacturing technologies?
One of the challenges is to have this heat affected zone between these two technologies, because the approach should be without any heating process after the combining of the two technologies, and then we have a quite strange effect on these heat affected zones regarding the failure of the structure, and that is also one of the main parts that we have to tackle within the virtual development process that we want to achieve.
But that would maybe, you could also investigate cold spray and depositioning.
Would also be possible, yes.
Okay. To all of you, where do you see the biggest potential for your technology to be applied in mass market? Are you also aiming for micromobility, smaller vehicles, larger commercial vehicles? And where do you see future research needs? We are currently discussing quite a lot of topics in context of 2.0 and road mobility, where lightweighting is not that exposed. Maybe where do you see research needs, and where do you see the market potential of your technology?
Well, as in FLAMINGo, I think our technology is really connected with the recyclability factor of aluminum. So as soon as there is a way to recycle aluminum with a very good percentage, also dealing with different alloys, then we can consider the use on vehicles to increase a lot. And probably the smaller vehicles can be a more interesting entering point for such technologies, because they are more flexible in adopting this kind of new approaches. For example, HPDC on a small vehicle can be used to cast the entire main structure. Mm-hmm. And that could be done with aluminum, and the same approach that we adopted in FLAMINGo can be further extended to magnesium in the future.
And the research needs? Where do you see further research needs?
Well, combination of nanoparticles and aluminum alloys. So we didn't explore all the combination. We were more into high-strength aluminums, Series 6, and the combination with nanoparticle basically was somehow hindered by the already good effect of the microstructure that the aluminum Series 6 have. What we want to try differently is to use low-grade aluminum, so like aluminum can type, which has a very few other elements in it, can be recycled more easily, and the strengthening effect can be obtained by the inclusion of nanoparticles that are removed at the end of the recycling.
Mm-hmm. Okay, and Christian?
For our approaches, I think one is to use these hybrid technologies for battery cases, to edit there some functional features within a 3D printing process. Mm-hmm. That could be one part. The other thing could be to use that technology especially for lightweight vehicles to improve the crash performance, because there we have the problem lower mass from the baseline on, and the compatibility to these high mass vehicles actually produced is quite big, and so there are these improvement and this adaptivity from our technology can be a game changer for the safety improvement of these light vehicles. And future research needs, especially on the optimization part of the recycled aluminum. I think you mentioned it yesterday in the panel discussion, when we will use more of these recycled materials with higher recycling rates, then the base material has to be designed or developed a little bit different in the designing process of the structure. Mm-hmm. And therefore I think should be also it will be also a huge lack of knowledge how to improve the designing process and the optimization process.
Okay, thank you very much. Any further question from the audience? There is one and two. Yeah, good. So we steered at least a few questions.
Yes, thanks everybody for your presentations today. I'm Graham Seaton from National Highways in the UK, and this might be a stupid question, but is there any scope for applying these materials and sort of design and manufacturing techniques to roadside infrastructure? I'm thinking of such things as signposts, lighting columns, perhaps safety fences. What are your thoughts in regards to that possible application?
So from our side, I think recycled aluminium is suitable for that use. It should be possible to use it on that components or on that structures. Doesn't matter if I use it in the car or outside of the car for crash safety. 3D printing, I think the cost factor and is there much more higher than also in a vehicle. So you can use such technologies easier directly on the car than on the infrastructure. But I think the use of recycled aluminium, why not?
Yeah, indeed. I can confirm we have looked into the different figures in cost of manufacturing, and the main cost for aluminum is the primary production. So after that, it's downhill. But there is probably not yet a completely and well-developed a way to collect the different streams, different kinds of aluminum, and have a full circularity of each of them. So also the high performance aluminum we were using can reach, in some cases, a recyclability of 90%, but in a closed loop. If they start to be mixed with other kind of aluminum, the recyclability goes down quite quickly. In FLAMINGo, we measure the recyclability of 42% using a standard approach, not a fully circular approach for aluminum. So our Series 6 aluminum were mixed with other aluminum of the same series, but not exactly the same composition. So a few percentages of iron, for example, determines that it cannot be reused in full for the same purpose. So yeah, it boils down to that. If we can recycle with a lower price than steel, because also steel can be recycled, then of course can be used.
Yeah.
Thank you. Alfonso from the Barcelona Supercomputing Center. My question is more in the context of future further research in new materials or improved materials. Do you mind if high-performance computing or simulation, such as deep materials networks, could help to accelerate or to facilitate the resolution, the solution of coupled problems regarding micro-scale to macro-scale new materials research?
What's the answer?
I think computational power is always an enabler for using of different materials, especially when you are reinforcing materials, when you adapt or develop a new material. Our bottleneck is sometimes when we see here, especially then for future crash scenarios, when these test metrics or simulation metrics widened up, and we have to simulate thousands of different full vehicle crashes. So this is only the last part of the game, let's say, or of the development. We have to do that also on the material side, and more computational power, more computational possibilities that we have, I think will speed up dramatically also the development process of the material and the usage in a final structure.
Do you want to add?
Well, yeah, I can give some thought about from my experience. It's a great possibility to have the modeling at different scales, especially when you have already some good experimental work done and you need to fill in the gap in between the different experiments. So we tested one series of aluminum with one specific silicon carbide. What if we change the size of the carbides? What if we change the composition of the alloy? We can have experimentally a limited capability, but from the point of view of material design, it can be expanded. It really boils down into how much you constrain the model, because sometimes the assumption you make drives to something that is not the reality.
If I may add some of the aspects already have been mentioned, but in terms of, let's say, design of experiments, if you, particularly when you go to recycling, where let's say, the alloying elements have a significant impact on the material properties. We see it in aluminium, in other metal parts, but also in view of plastics, where the quality is even more impacted by secondary sources. You have to apply computational measures to predict the properties, to reduce the number of experiments to validate and to find the right combination. I think there is no way around, otherwise it will not be cost effective. So there is a high need for advanced material simulation, particularly in context of secondary material flows. It's my opinion. Further questions? If not, Katerina, do you have any further questions?
No, I mean, this is not exactly my background. So, I would like to leave this session and try to understand a bit where the industry stands, how, when we should expect these developed materials and vehicle components with aluminum, with nanoparticles to be in the market and be accessible to the broad audience, to the people?
Well, in FLAMINGo, we operated at industrial relevant scale. So all our material processes. Yeah. So well, of course, it was not a car that a standard car. It was a smaller utility vehicle, but all the process in between has been done at an industrial relevant scale. So we can start basically soon, as soon as there is a space, economical space for that,
Okay, so
to introduce these materials in the market. Because the processes are all tested and also
No, I know that
safety
you work
requirements.
in the real scale and you produce the vehicle parts in reality, but it's, you know, Renault,
Someone needs to take
VW, Tesla, I don't know.
Need to push a bit more on the marketing side.
Okay. Christian, Raquel?
I think in FLEXCRASH it's not the same, but we are on a comparable level in the should be on the end. So we can provide a technology, we can provide tools and methods to implement these technologies in a industrial scale. Bottleneck is always the implementation of these technology when we are using 3D printing on a high volume market, but perhaps a few of our technologies will be integrated in the near future.
If I may add, don't forget that findings from such collaborative research projects regularly are being introduced in the product development phase of the industry. You don't always recognize that it's coming particularly from one of these projects. So I think the lessons learned by the partners here that will be definitely used in improving their development process, and therefore it will automatically make an impact. So it doesn't matter in that case whether a certain component is made of nanoparticle enhanced aluminium, but the knowledge they gain will be used, and this is something which you may then see in 3 or 4 years.
Correct.
No, thank you for the input. I understand that yes, it's a research project, it's being developed, and it's important to gain knowledge. But overall, also from the discussion yesterday in the plenary, we saw that automotive is going towards adopting more circularity principles. So all this, it's going up in, you know, people will be searching for FLEXCRASH, FLAMINGo, Salient, and so on. Thank you very much for the conversation. Thank you to our panelists. Please, a warm round of applause to them. And also thank you to Thilo Bein from Fraunhofer for steering the discussion. Again, a round of applause.
And then I have to thank you for moderating this one. You are from the agency, you're the most relevant one, but thank you for I think everyone here and also the audience, I think appreciated your moderation.